All right. In our last class, we introduced L'Hopital's rule, which told us that under some conditions on f and g, that will always actually be satisfied for us. If you're trying to evaluate the limit as x tends to a of a quotient like this, which is either of indeterminate type 0 over 0 or of indeterminate type, looking down here, plus or minus infinity over plus or minus infinity, well, you can evaluate that limit as x tends to a by evaluating the limit as x tends to a of the function obtained by differentiating the numerator and differentiating the denominator. So in either case, the limit of the quotient is equal to the limit of the function obtained by differentiating the numerator and differentiating the denominator. As we said in our last class, remember, you do not want to use the quotient rule to differentiate the entire function f of x over g of x. That is not what the rule says. You want to just differentiate the numerator and differentiate the denominator. Also, remember that if you want to use L'Hopital's rule, it specifically needs to be of one of these two types, 0 over 0 or plus or minus infinity over plus or minus infinity. So in our last class, we did examples where we used L'Hopital's rule to evaluate limits of type 0 over 0 and type infinity over infinity. We also did some examples where we evaluated indeterminate forms that looked like infinity minus infinity. Well, now we want to do some examples of the indeterminate form 0 times infinity. So remember, this is indeterminate. It's not necessarily 0. It's not necessarily infinity. It could be 0, could be infinity, or it could be any real number at all. All right, so what's the tip? Well, when we have a limit of type 0 times infinity, we're going to be taking the limit of a product of two functions, f and g, with one term tending to 0 and the other term tending to infinity. And the trick is to write the product f times g either as f divided by 1 over g or as g divided by 1 over f. Notice that f divided by 1 over g is in fact, well, if I were to divide by this fraction 1 over g, I'd multiply by the reciprocal g over 1. F over 1 over g then is equal to fg, and similarly fg is the same as g over 1 over f. Now, the new limit is going to look either like 0 over 0 or infinity over infinity, and so we'll be able to apply L'Hopital's rule. All right, so here's an example. This is the fifth example, in fact, for us in the L'Hopital's rule section. So we're supposed to take the limit as x tends to 0 from the right of root x times log x. So the first thing we should do is consider what type this is. In particular, notice that you can't evaluate the log function at 0. 0 is not in the domain, so we can't just plug the value 0 in. So what's happening? Well, our first term, as x tends to 0, from the right, root x is going to tend to root 0, which is 0. And the log x, what happens to that? Well, as x tends to 0 from the right, remember log x is tending to minus infinity. So this looks like type 0 times minus infinity. So write that down. This is type 0 times minus infinity. Okay, so what is our trick? Our trick is to write one of these terms, either root x or log x, in the denominator as its reciprocal. So what are we going to do? Well, we have to either decide to put root x in the denominator as its reciprocal, or log x in the denominator as its reciprocal. And usually you want to pick the one whose reciprocal is going to be easiest to differentiate. So in this case, I'm going to put the root x in the denominator as its reciprocal. All right, so what is this equal to? It's equal to the limit as x tends to 0 from the right of log x over 1 over root x. And if we look at this, we now see, well, the numerator, log x, that's still tending to minus infinity as x tends to 0 from the right. And as x tends to 0 from the right, this 1 over root x, well, we're going to have 1 for any x bigger than 0 and close to 0. That root x in the denominator is going to be a very small positive value. 1 divided by a very small positive value is going to be very large. This limit here then is going to be plus infinity. Okay, so this is of type minus infinity over infinity. And that is the sort of limit to which we can apply L'Hopital's rule. Now, because I'm going to want to differentiate this denominator here, this 1 over root x, let's just rewrite this as x to the minus 1/2. So here we are, we've rewritten this. It's still the same function, so it's still of type minus infinity over infinity. So we can apply L'Hopital's rule. And how do we do that? We differentiate the numerator. That's 1 over x divided by, and differentiating the denominator, we're going to have minus 1/2 x to the minus 3/2. All right, the next thing that we want to do before we assess what type of limit we have now, always after applying L'Hopital's rule, so after differentiating numerator and denominator, you should simplify your new function as much as possible. All right, so this is going to look like, so notice that denominator is minus 1 over 2x to the 3/2, and so we can write this as minus 2x to the 3/2 all divided by x. And now we're taking the limit as x tends to 0 from the right. We don't actually care about the function at 0, just for x close to 0 and bigger than 0, so we can cancel those x's. And doing that, what do we get? We get, this is equal to the limit as x tends to 0 from the right of minus 2x to the 1/2, which I could write as root x, and no problem with taking this limit. 0 is in the domain of this function, which is continuous, so we can just evaluate this limit at 0, and we get minus 2 times root 0, which is 0, and so that's the limit. All right, here's another example. It's the limit as x tends to minus infinity of x squared times e to the x. So what type is this? Well, as x becomes large and negative, x squared becomes large and positive. So first term is tending to infinity, and as x becomes large and negative, what happens to e to the x? Well, just remember what our graph of e to the x looks like, and we see that as x becomes large and negative, e to the x gets closer and closer to 0. It's always positive. It never actually equals 0, but it gets closer and closer to 0, so our limit as x tends to minus infinity of e to the x is 0. So write that down. Okay, so this looks like infinity times 0. Well, as before, we want to turn this into the type of a function, the type of limit, rather, to which L'Hopital's rule applies. So we'd like it to look like type 0 over 0 or type infinity over infinity. So we're going to use the trick that we used last time. We're going to put one of these two functions in the denominator as its reciprocal. Okay, well, which one? Well, whichever one we think is going to make for a better differentiation. In this case, I'm going to try to put e to the x in the denominator as its reciprocal. So what are we going to have? So we're going to have this is equal to the limit as x tends to minus infinity of x squared over 1 over e to the x. All right. And we'll check and see how this works out. I will say, if you decide to put one term in the denominator as its reciprocal, in this case I chose e to the x, and things don't seem to work out well, in that case you can start over and put the other term in the denominator as its reciprocal. Well, in this case, let's just notice 1 over e to the x. Maybe I want to just rewrite that a little bit and notice that this is actually the limit as x tends to minus infinity of x squared over e to the minus x. And now, what type do we have here? All right, as x tends to minus infinity, as before, x squared is going to tend to plus infinity. So our numerator is tending to infinity. And what's happening to e to the minus x as x gets large and negative? So if x is large and negative, minus x is going to be large and positive. What does e to a large positive number look like? Well, it becomes arbitrarily large. This e to the minus x is tending to infinity. All right, so we now have a limit of type infinity over infinity. This is the type of limit to which L'Hopital's rule applies. So I'm just going to put an H here to indicate that we're employing L'Hopital's rule. Get the limit as x tends to minus infinity of 2x over minus e to the minus x. All right, differentiating numerator and denominator. Now what's happening? Okay, so as x gets large and negative, 2x is going to get large and negative. So our numerator is tending to minus infinity. And what about the denominator? X gets large and negative, minus x gets large and positive. E to the minus x, just as above, gets large and positive, and then we have this negative sign, so it's tending to minus infinity in the denominator. All right, so again, this looks like the sort of limit to which L'Hopital's rule applies, and it doesn't look like we can really do any algebra with this. It doesn't seem that there are any simpler methods for us to use at this stage, so we're just going to apply L'Hopital's rule one more time. So this is equal to applying L'Hopital's rule, the limit as x tends to minus infinity, differentiating the numerator, so differentiating 2x, we get 2, and then differentiating the denominator, we'll have minus the derivative of e to the minus x, that's a minus and a minus, which is a plus, and we have minus e to the minus x in the denominator. Well, what does this look like now? Well, let's take a look. So the numerator is just tending to 2, and what's happening to this denominator? Well, as x becomes large and negative, as before, minus x becomes large and positive, e to the minus x becomes large and positive. So for all x's we're considering, large and negative x's that is, our function looks like 2 divided by a huge positive number, which is going to be very close to 0, and taking the limit, our limit is in fact going to just equal 0. That's it.